Okay. Hello, Internet. Welcome to the Groundup Coder. So, I wanted to share with you guys today something cool I think I've been working on. Yeah, so I've been working on my C compiler, but like I've just as I've been working on my C compiler, I realized you know if I work on my if I grow the C compiler, it's eventually just going to turn into an operating system, and I think that's kind of what happened. So let me just show you kind of the stuff it can do. It's got a Minesweeper. It's got a little terminal. It runs real BusyBox, which I think is pretty cool. Like, oh man, I imported granted, Hush is probably the easiest shell you can possibly port, but it's a real shell. And then you got Quake. Yeah, but it takes your pointers. I'm not gonna keep that open. And then I got a little paint program here. I got a notepad. I got a little 3D demo that runs a program WebGPU. Game Boy emulator with no cartridge. Doom. Of course, we gotta have Doom. We got calculator. We got Super Mario. We got Pokemon. Okay, and it's starting to get kind of crazy. So I'm gonna mute the site here. But yeah, I don't know. I think this is pretty cool. But yeah. Oh, and then one other thing is that you can use the C compiler inside the OS as well. So if you do cc hello.c hello, you can run hello. Anyway, yeah. So I want to talk about Groundup Coder OS and kind of what happened. What happened is as I was implementing my C compiler, it was very natural. Once I had most of the standard that I wanted, to start implementing the POSIX standard. And then as I started implementing more and more of the POSIX standard, I was like, well, I might as well just have a full operating system, and wouldn't it be just cool to have it on the browser? So yeah, that's what happened. I kind of wanted to talk about some of the stuff that I implemented. So here it is. So yeah, POSIX on WebAssembly, or what is an operating system anyway? So here's the thing, right? Can I call this an operating system? It's running in the browser, right? I mean, look, it kind of looks like one, but if it's not on bare metal, is it really an operating system? So yeah, so here's just what traditionally an operating system does, right? I think the one that everybody kind of thinks of first is the hardware abstraction layer. It's kind of the drivers and kind of the way that you manage the way you interact with the rest of the hardware. I guess in my head I'm thinking the most classic stuff is the USB. If you're doing stuff from scratch, you kind of see how much work goes into just being able to talk with a USB drive, which seems kind of counterintuitive, right? Why isn't that simple? But it's the reality of the world. And then scheduling, yeah, scheduling, right? You got multiple processes running, memory management, which arguably you don't have to do so much of when you're in the browser, when you're working on WebAssembly. File system access, yeah, you somehow you need to solve that problem somehow. Granted, that problem is very different when you're trying to solve it in the browser, but it is a problem that's going to be solved. Inter-process communication, right? Oh yeah. So when it comes to processes, right? I have the calculator here. Let me list all the processes running here, right? And then calculator is a process listed by PS, and then I can kill it, right? Boom, it died, right? So how does this program here know about that program over there, and how do you get it to respect the kill signal, that kind of stuff. Yeah, and then you need some sort of interface. You kind of for an operating system, you kind of expect there to be some way that you you can interact with all the programs running on your computer. And so what is POSIX, right? So I kept saying POSIX. You might be like, what is it? Well, like, so an operating does all of these things, right? Like the, hardware abstraction, scheduling, whatever. So POSIX is kind of, just to put it like completely 100% oversimplify, is just kind of a set of standards in terms of like how the operating system will interact with programs that run on it. And like, people who are using it, right? So like, so POSIX defines, for example, some system calls, and like if you're writing a C program, if you're writing a C program for a POSIX environment, you're guaranteed to have certain set of functions that the standard library itself might not have. For example, the C standard by itself does not give you any way to list directories on its own, but POSIX gives you a few extra functions to do that. And like there's some agreement on what like a shell is supposed to look like, and like what set of command line tools are available, like PS or LS or whatever. And then like some basic concepts on like what is a process, right? Like in theory, not every operating system needs a notion of a process, right? I guess maybe you need some notion of a process, even if it's like a single process, right? But like POSIX also kind of comes to an agreement on like, okay, like, you have the concept of signals, right? Like if I can, this kill signal I sent to the calculator, right? Like there's kind of an agreement on like, okay, well, it is possible to send signals that will kill the program or like more gently SIGINT the program, right? Or the file system and I/O, like how are guest programs gonna interact with the hardware resources the operating system provides, right? So POSIX kind of gives you that stuff. Anyway, so what does Groundup Coder OS do and not do? So like, it does have a notion of processes, which like, again, granted, it is a lot easier on WebAssembly because essentially the way I'm treating this has been like, web gives you this, there's this notion of a web worker in the browser context. Well, it's kind of tied to threads too. Like, it handles processes. There's a kernel kind of that keeps track of like a table of processes and the resources attached to them. But right now, I do not implement threads. It's not like fundamentally a blocker per se. Like there's no fundamental thing that makes it impossible to implement threads here, but I avoided doing it because, like a lot of programs, you can actually get away with not having threads. And like the parallelism I already got for free because web workers actually are kind of parallel. They do run parallel. And that kind of ties into SMP. SMP is like kind of the hardware stuff that you have to deal with to get parallelism to work. But because we're working in the browser, the host system already kind of takes care of that for us. Sound also, right? Like that has to be handled somehow, right? And so this is kind of also owned by the kernel. Like there's one web worker inside the GUPOS system that funnels the sound stuff. Like pulls in all the sound stuff together so that it's kind of all mixed correctly. We have a compositor, basically, right? Like each of these programs themselves, they just think they're writing to one surface that belongs to them, right? But like you do need like some sort of, the operating system itself needs some sort of like, logic for how these windows all come together. And then like if you have these windows, right, and the little buttons, and resizing, like that system also has to be kind of handled by the system as well. File system is a funny one because I thought like there's this thing in the browser called OPFS, or what does that stand for? Something. It's like it's an API in the browser that lets you kind of like interact with like a virtual file system, and it's persistent, right? So if I reload the page, that file system still sticks around. But the reason I decided not to use it directly. Number one, because the file system API requires like listing files to be an async operation, right? So if I go into like a folder here, and then I want to list, okay, what are all the folders files that are available inside this folder, listing them in it, like that has to happen in JavaScript land. And in JavaScript land, it gives you a promise, right? But that means that the WebAssembly code, because all of these programs are in C, right? So all of these C programs, they're in WebAssembly. And so that means that the WebAssembly code needs to actually wait for a promise to resolve. Like it needs to like the moment it needs to list a directory, it needs to pause, wait for that promise containing the list of directories to resolve, and then continue, right? So that's actually like, you know, kind of a pretty big feature, because it's kind of difficult to implement in the browser, called JSPI, and or JavaScript Promise Interface or something like that. And actually, like, I think Chrome has it. Chrome definitely has it. I think Firefox has it too, but Safari does not. Or like the mainstream release as of July 2026, the stable release as of July 2026 does not have JSPI. And you know what? I just wanted this OS to just run on my on my phone as well. So I looked for a different solution, which was like kind of creating a fake block file system. So like on a real operating system, you kind of use something like ext4, or if you want to keep things simple, maybe like ext2, or even simpler, maybe like fat, you know, a fat file system or something, where like you know, you use a file. Usually, you use one of those because if you're working with real disk, there are some like restrictions on how the hardware like will interact with what you're doing. But you know, when you're working with OPFS, I actually don't know. Like, I also wonder if I should like measure the impact that like arbitrary random access of like, you know, edits in a file will actually like hurt disk usage. I'm not sure, but I think a lot of it gets kind of smoothed out by the operating system layer in the middle, because it's not like, even then, it's not like I'm kind of, the edits don't go directly to to disk, because I'm in the browser layer. Like the host operating system will use a real disk file system, right? Like, you know, I forget what Mac uses, but like, if you're on Linux, you'll use the ext4. If you're on Windows, you'll use NTFS, and those file systems will like have their own way of writing to disk that will respect the properties of the disk. So, for example, like if you're, you know, on SSD, well, you know what? I'll just leave it there. Maybe if I need to explain that, if people are curious, maybe I'll explain that at some point in the future. But basically, file systems have a like thing you have to respect. Anyway, so there's and then you have shells, which, yeah, I guess I showed here. We have real BusyBox Hush shell running, but shell is also interesting because we don't have fork and exec. So what fork and exec are like, yeah, so if you're not familiar with them, they're like kind of like crazy functions. So fork and exec, these are system calls. So basically, like, they're not part of the C standard library, but they are part of POSIX. And if you're in POSIX, strictly speaking, if you are real POSIX, you're supposed to implement them. And what they do is, like, fork is a function that when you call it, it basically creates an entire copy of your process and then runs it. right? And the function will return a number, I think it's 0 or 1, depending on like, or maybe it's a PID, 0 or PID or something. I forget the exact contract, but like, depending on the return value of the fork function, you can tell whether you're the parent or the child, right? So it's a way of like creating a new process that is literally a copy of the original. And if you've never like heard of fork and exec before, you might be wondering like, why would this ever be like a useful function, right? Like, why do you like, how often do you want like a literal clone of the process you're running? Well, usually, I want to say usually, I don't know, maybe there are just genuine, situations. Maybe like when you have like a multiplexer or something, maybe you do want fork. But like, for the most common use cases, what you often want to do is follow it with an exec. And exec is also kind of a crazy function, if you think about it. So exec is a function where like, you have a process that's running with a certain program, right? You compile a certain C program, and then you're running it. But when the moment you call exec, you pass it the path to another program, like that's already compiled, and then you replace the executable of your current process with that new program. I don't know if I've just done the best job of explaining that, but like basically fork means you're cloning your current program, so that there are two processes that are running. And exec means that the program attached, the executable attached to your current process has been substituted. Which, like, on the face of it seems kind of crazy, but you combine them. Usually what you're doing is you're combining them to like if you use subprocess in Python, essentially, like, that's what they're useful for doing. And the reason why I split it up this way, having fork and exec, there's a historical reason, which is like, in early Unix, it kind of made sense to do that when memory spaces were very small. And then the modern kind of like, and kind of the functional reason why you might do this is that doing it this way means that between fork and exec, you can really customize your like state. So like fork will allow you to, I feel like I forget that, like, there's some rules on like which file descriptors you inherit from your parent process. Like if you open some files in the parent, you kind of get a copy of them in the child, but then like, I don't know. I should stop talking about this because I'm not really like an expert in that. But yeah. Anyway, the main problem is that both of these require you to do some crazy you need to be able to do stuff on the process that WebAssembly itself and web in general generally forbids, in part because like it is kind of difficult to implement them in a way that's safe and like efficient. So like essentially what you need is, right, for example, like if you think through it, like for fork, what do you need? Well, you need to be able to like create a copy of that program with all of the memory associated, like all the globals and locals, like and all the memory copied over, right? And not only that, you need to have the call stack be the same, right? Like in WebAssembly, you actually don't get direct access to the call stack, right? And you need to be able to, your child process needs to be able to jump exactly into the point in the executable that the function was at when the fork function was called. So that means that like if you call fork in the middle of your function, you need to be able to jump directly into the middle of that function with all the call stacks nested on top of it, right? Yeah, so it's just like there are ways to do it, like emscripten even kind of like does it as well, like as well as a few other people trying to tackle this problem, but like it comes with a cost. Like on a real operating system, there are many like cute tricks you can do to make this efficient, which like all modern. I want to say all modern operating, like POSIX operating systems, like on real hardware will usually do. But like that, they can do that because they have access to raw hardware and they have primitives that like, a lot of people would consider kind of a little bit dangerous. Anyway, that was kind of a rant. Anyway, so like shell is tricky because of because we don't have fork and exec. And shell, like kind of the main thing a shell does is, well, fork and exec, right? It starts other processes, like you run, you know, other programs in the shell, and that's kind of what fork and exec are for. But the way that I kind of work around them, and actually like the POSIX standard itself later added POSIX spawn, which is like one function that will create a new process using like a compiled executable. And actually in my own GuckOS, I have a little bit more general of a primitive, like dunder spawn, and I use that to, so yeah, so this is Hush mostly. It is mostly the Hush implementation for BusyBox, but parts of it have been patched so that it doesn't use fork. I think, yeah, instead of vfork or whatever, it just uses spawn directly, which is a thing. Yeah, isolation. Yeah, I guess like we get that from web workers, and then signals. So signals and preemption, they kind of go together as well. So like, so signal is like this kill signal I sent, right? Like while a process is running. So normally how a POSIX signal works is like when a program is running, you can kind of stop the program, like get the program to pause itself, like handle a thing that's happening, and then have it come back, right? But the problem is on WebAssembly, you kind of, you don't have that primitive, right? So like in WebAssembly, if you have a web worker that's doing like tight computation, right? Like it's not printing anything to the screen, it's not talking to any other systems, it's just like crunching numbers for a very long time. Those kinds of processes cannot be preempted. You can't just like say, hey, pause your calculating and then handle this thing first, and then you can go back to it. You can kill the process. Like killing a process is still doable in WebAssembly, but you can't do a thing where like you pause it, you suspend it here, and at an arbitrary point, and then we'll do something else and we'll come back. So the way kind of it's faked here is, like most programs aren't all just stuck on computation for a very long time. So anytime the process will talk to the kernel, like ask for like, you know, like every time the screen changes, like in an emulator here, like it needs to, you know, make a kernel call to like say, hey, my screen updated, right? So so for that, whenever that happens, it allows a signal to kind of get in there and then do its thing, and then, you know, resume after that. Yeah, so that's the thing. Yeah, so that's kind of some of the bigger pieces. So there are similar projects. So my first thought actually was like, POSIX on WebAssembly, doesn't emscripten already kind of do that? But the thing with emscripten is like, you can certainly use emscripten to kind of build the pieces, but I think by itself you get like, it's all private, right? Like the file system, I think originally it was like IndexedDB or whatever, but now that there's OPFS, I actually don't know if they've moved over to OPFS. But it's like a single process, like you can get one compiled program kind of basically in there. And then if you really wanted to have some kind of like, you know, shell and whatever, like you kind of have to build out that system yourself. You have emulators that can kind of do this, like what is it, like JS Linux, or is it JS Linux? V86 or whatever, where like there's you emulate like an x86 or ARM CPU. Like that will get you the real thing. Like you can actually, you'll be able to run like, you know, Linux just as is basically. But that means like you have to like you have to simulate a whole separate computer, which, you know, that's going to slow things down a lot. And then I've seen these in passing. I'm not sure of the details, to be honest. But one thing like I think I've heard is that like, so projects like WASIX and BrowSix, they have real, like they're actually like targeting real POSIX. Like they want to be properly like POSIX compliant. which means that they actually have to implement fork and exec, which are quite expensive. And just like, not only are these expensive to do in WebAssembly, like they're also hard to do. Like I'm just sitting here thinking about, well, how would you do that? How would you implement like fork and exec? Like I guess one way is like you could like, you know, for any program where you know you might have to fork, you might have to dump all of your like memory into like all of your local variables into linear memory. That's going to slow things down. I mean, that part, it might not, that's not logically hard, but that would just slow things down. And then, you know, and then not only that, the more expensive part would be like, you'll have to have some sort of state machine probably. I'm not sure how you could avoid a state machine. Maybe you could, but I'm just imagining like, well, you need some way to like build up the stack. When you do the fork, the child process needs to be able to build up the stack and enter that location, exactly where the fork call happens. Like, I would imagine you need like, you know, you need some sort of state machine to do that. And exec as well. Exec is also like, well, exec, maybe that one's not so bad. Yeah, you like exec, you could just replace, you could just create a new like WebAssembly instance and then just start at the right place. Yeah, still like, you know, that combination is tricky, right? But yeah, that's kind of it. Oh yeah, and you can also kind of edit the slides. Huh. Anyway, I thought that was pretty cool. Yeah, thanks for watching.